I think the rain is messing everyone up.
So,
Especially on Monday.
we are going to focus
Oh, it's a rainy Monday.
on trig identities.
5-day week. This is like the ideal Monday right now.
So it can only get better from
Miss
here.
Allison just told us we have 2 more.
Go.
So we are going to start our second trig unit, which is dealing with trig identities and trig equations. So far with trig, we've worked on unit circle and understanding the unit circle, how to use it, what to do with it, and then graphing. And we know with every unit so far this semester, we've done simplifying, solving, and graphing. Well, we're working on more of the simplifying, and we'll work on the solving now. So we're going to start with the idea of trig identities. This is not on the test that we're having Thursday. And the only reason we're doing that test on Thursday is to give you the time you need to take it. I'm not going to give you a test on a Monday because, well, that's just not cool. And I figure the block day is a better day to do that. So that's why we're doing it on Thursday. So what we're going to work on today theoretically won't take the entire hour. But at the rate we're going, it might. And then tomorrow is really just work time. So that time tomorrow, we'll answer some questions on your review, and then you'll have more time to work on whatever review will help you best for your test, as well as finish up trig identities. So an identity is an equation. Oops. Yeah, I didn't realize it wasn't down. Identity is an equation.
Wow, that is so much better.
Because there's no reflection.
Genius. It was also just starting to give me headaches.
Yeah, it would give me a headache too. An identity is an equation that is true for every number in the domain of the equation. That sounds terrible and not super useful. But let me give you some examples of an identity. We have what we call the additive identity. If I take and add 0 to any equation, if I add 0 to any equation, have I changed my equation any? No, that's called the additive identity. I can add it to any equation and it's not going to change it. We have a multiplicative identity, which would be 1 times the number, and that 1 times whatever we multiply it by is not changing my problem any. Those are what we call identities. Well, in trig, we have identities as well, where it's an equation that's true for all numbers. It means it makes the equation true. Okay? There are 6 that we're going to look at that we've already seen before. This will help because you have this on your... Oops. I made a mistake on the note sheet. I see that now. Shoot. Okay, first one says sine of x equals 1 over. What is it the reciprocal of? Do you remember? Sine is a reciprocal of what? You've had to do this a million times with the unit circle. Not cosine. Cosecant. Cosecant. Remember, if we take the cosecant and we make it the reciprocal of it, 1 over the cosecant gives me the sine. What about the cosine? Secant. What about the tangent? Cotangent. These are what we call our reciprocal identities. Sine of x is equivalent to 1 over the cosecant of x, which means the cosecant of x is equivalent to 1 over the sine of x. What about the secant of x? Cosine. And this is where I made a mistake because that should have said cotangent.
Thank you. Oh, that's cool.
If you can spell Cotangent of x
Equals 1 over 10.
it does equal 1 over tangent. These are called our reciprocal identities. We have two ratio identities. Let me give you one of them. Tangent of x
Gotta be.
is the sine of x divided by the cosine of x. We remember doing this on the unit circle. Tangent of x is sine of x over cosine of x. So, what is cotangent of x? Cosine of x over sine of x. You guys, these are not new. These are the same identities we've looked at. We're just going to formalize them as an identity, which is going to help us verifying or simplifying identities. Okay, the three that are going to be new really only stem from, or the easiest way to remember them is by knowing one of them. Because if we know one of them, we can find all three of them. So we're going to start with Pythagorean identities. If you say Pythagorean, what do you think of? Triangles. And Pythagorean theorem says what? A squared plus b squared equals c squared. Okay? I've given you one of the Pythagorean identities. I gave you the one that says sine squared x plus cosine squared x equals 1. But let's talk about where that comes from. Let's go back to our unit circle for just a moment. If we go back to the unit circle or to the idea of those triangles that we built in our plates. We created right triangles, right? Pythagorean theorem. A squared plus b squared equals c squared. On a unit circle, what's my hypotenuse every time? I happen to have a unit circle here. It was gifted back to me. I'm real excited about it.
Is that yours?
Yes, it's Avery's. What was our radius?
360.
That was the full.
She emailed me back too.
What was this length?
60.
Not x. It's 1. It's called a unit circle because the radius is a unit. So I'm going to draw this radius here as a unit 1. I would.
Should we?
Sure.
Well, like, what does it do?
It's going to help you remember it.
Nothing.
Math is so off.
All right.
I don't even know. Mia, stop. Do like smart with a pencil in my ear. Looks like a contract.
It's a thing Martin might do.
Martin would walk in like a pencil on his.
So if we look at this triangle, the y value and the x value had names. Do you remember on the unit circle when we looked at the y values, this one doesn't have all of our ordered pairs, but when we talked about the x value here, what did the x value represent? If we look at an ordered pair on a unit circle, what does the x value represent? X represents what? Look at your unit circle, might help. Do you have a blank unit circle? Oh.
If I can find it.
Oh.
Job in English.
What does our x value represent? Oh, there it is.
I found it. Yeah. Okay.
X value.
I already knew that. Isn't it cosine?
It's cosine,
I knew it.
right? Isn't our x value
Oh, yes. I didn't realize that's what you looked like right here. I was like, X is cosine, Y is sine.
y is sine? And we said this is a right triangle. And the Pythagorean theorem says we take a squared plus b squared equals c squared. Sine squared plus cosine squared equals 1. That's where the Pythagorean theorem comes from. This is really just a squared plus b squared equals c squared. But we're using a unit circle. Okay. Okay, so if you know this Pythagorean theorem or this Pythagorean identity, you can get to the rest of the Pythagorean identities, and here's how. Okay, all of them are going to base off of the sine squared plus cosine squared equals 1. That's going to be my base. So watch what I'm going to do to start these problems. On each of these problems, I'm going to start with the idea of sine squared x plus cosine squared x equals 1. If I want to get a tangent squared, remind me the ratio of tangent that uses sines and cosines. Sine divided by cosine. Sine divided by cosine. So what I'm going to do is I'm going to divide everything by cosine, or cosine squared. So I'm going to divide each of these by cosine squared. Well, we already said that sine squared divided by cosine squared is tangent squared.
No.
Cosine squared divided by cosine squared is 1. There's my tangent squared plus 1. What is 1 divided by cosine? Well, we've done that up above in my reciprocal identities. What is 1 divided by cosine? This is the secant, and because they're squared, we're going to call this secant squared x. So 1 plus tangent squared x equals the secant squared of x.
It's
No memorization.
What is this?
Nope. If you know sine squared plus cosine squared equals 1, we can get to any of these Pythagorean identities. So try the next one and see what you get. See how you can come up with, using the fact that we're going to start with sine squared x plus cosine squared x equals 1, and come up with 1 plus what cotangent squared x is. 2. What did we get? What did we divide by on this one? If we're trying to get cotangent squared, I need to divide both sides by sine, or everything by sine squared x.
Wait, why did we divide by sine x?
Because my goal is to figure out cotangent, and I know cotangent is cosine over sine. Over sine is what I'm going to divide by, is that over sine. So sine squared over sine squared is 1. Cosine squared over sine squared is our cotangent squared. That's what we were shooting for. That was our goal. And 1 divided by sine squared is what? Cosecant. So then I know that this is the cosecant squared of x. So I have 3 Pythagorean identities, but they all come from that 1. The 1 sine squared plus cosine squared equals 1. So if you can memorize that or understand where that comes from, then the rest should be pretty easy. Okay. Now, because I understand I'm a math teacher and I'm a little bit dorky when it comes to things, I like puzzles. I know that should surprise nobody. These are all like puzzles. These next problems that we're going to work on are really just puzzles. We've got to figure out how we can verify or simplify, and those mean 2 different things, and I'll explain that in just a second. What we call our trig identities. And the way that we're going to go about doing that is based off of information that we're given. Okay, here's the frustrating thing, and maybe a good thing too. There is not a technique that we can try every time to make this work. Verifying trig identities, you may start it one way, I may start it a different way, and we both come up with the answer. I may have to start it one way and try it and go, nope, that didn't work, and do it a different way. That's okay. Okay? So, 2 types of problems we're going to see. The first type, it will say to verify. So when we talk about verifying a trig identity, if I want to verify a trig identity, I'm going to verify this expression right here means we're going to show both sides of the equation are equal. To verify means we show one side is equal to the other side. Okay? So we're going to start with some verifying, and then we'll go explain what simplifying means, and they're a little bit different. So to verify means we need to get both sides of the equation equal. So you can see this first example says verify that the sine of theta, secant of theta equals tangent of theta. My goal is to show that one side equals the other side. That's my whole goal. Here's ways we can do this. One, if we have a bunch of different trig identities, one of the things that we can try is rewriting everything in terms of sine and cosine. We can try multiplying. We can try using a Pythagorean identity when we see a squared term. We can try factoring. We can try splitting fractions, or we can try adding fractions. All of these are different techniques. And really, the best way to get going on these is just to start rewriting things. So let me give you an example. My goal is to verify this left-hand side equals this right-hand side. I can't change the problem at all. But what I can do is change what it looks like. Just like when we were adding fractions, or when we have to multiply by, or rationalize a denominator and we need to multiply by that magic 1. We're not really changing the problem, we're just changing how it looks. That's what we're going to do here. So I tend to start these problems by rewriting things in terms of sines and cosines. That's usually how I'm going to start these problems. So let's come here. Let's start with the secant. So let's start with this expression right here, secant of theta. Right now, it is not in terms of sine and cosine. How can I rewrite secant so it's in terms of sine and cosine? Very good. We know secant is equivalent to 1 over the cosine of theta. We haven't changed the problem any. I took the secant of theta and I wrote down the secant of theta in a different form. I used an identity, something that is true, to just change how it looks. Right? We know the secant of theta is 1 over cosine of theta. Why might I have done that? Okay, well, let's keep going. What about tangent? Can I rewrite tangent? Sine over cosine. Is anybody seeing anything yet? Tangent sine over cosine. What happens when I multiply this sine of theta times this 1 over cosine of theta? I get sine over cosine. And that equals the sine over the cosine. I have just verified that this expression is true. This is equal. This is called a trig identity. We have just verified it. We know it works. See? Kind of a fun puzzle. You mean yes? I know. All right, let's try this next one. You try this next one. Sine theta cotangent theta equals cosine theta. See if you can verify that trig identity. All right, what might you change on this one? I would start with the cotangent. If you were to rewrite cotangent, one over tangent or cosine over sine. I like rewriting it in terms of sines and cosines. I think it's a little bit easier. So we have this sine of theta equals cosine theta over sine theta equals cosine theta. Now everything's in terms of sines and cosines. What happens here? The sines do cancel out. This sine and this sine cancel out. Because sine of theta is really like having sine of theta over 1.
It works.
And then we get the cosine of theta equals the cosine of theta. And it does work.
Check mark.
See, that's not so bad.
So you're just trying to get, like, solving it to be cosine and...
Our goal is to get both sides equal, however that comes about. So, like on this one, we could have stopped here and noticed that that was going to be tangent, or we could just rewrite everything, and as long as both sides are equal, we're good. Jack?
Can you divide each side by sine theta?
Yep, you could. Yep, you could have. That's the point. These identities don't have exactly one way you have to start every time. It's like if you were doing an actual puzzle. Some people start with all the edge pieces first. Some people pick a color and start with that. Like, it doesn't matter. The end goal is to get that puzzle put together. The end goal is to get both sides of the equation the same. So as long as we're using good math, meaning we're not making up things, we should be good. All right. These two verifying the next two, we actually did already. We did them up here in the purple. So these ones, I'm just going to write here. I did them in purple. You may not have done them in purple.
It was the second and third one.
Yep. So we already did the verifying. We went through and verified these by going through and dividing everything by a common term to make them be the same. So those we have verified already. I forgot I wanted to do it at the end. All right. The next type of problem that we have is what we're going to call a simplifying. And all of the rest of these are simplifying. And when we simplify, our goal is to write our expression as one trig ratio if possible. So my goal is to get it simplified. So like, for example, you might be given the sine times the secant. My goal is to get it to look like the tangent. So write the expression as one trig ratio if possible. That's what simplifying means. Verify means show both sides are the same. Simplifying means write the expression as one trig ratio, and the process is the exact same. So let's look at some examples. What? On the back side. Do it. Great.
I still say Teresa's though.
All right. Here we go. I am going to start these problems the same way I started the front. I tend to like to put everything in terms of sines and cosines. So how can I rewrite cosecant of theta? What is cosecant of theta? Say that again. 1 over sine. And then tangent, if we rewrite tangent in sines and cosines, what is tangent? Sine over cosine? Oh, the signs cancel. So we get 1 over cosine, but typically we will then change this to be one trig ratio, which would be what? Secant of theta. That's a simplifying a trig identity. See?
I'm just kidding. Cold sarcasm is opposite.
Sometimes. We're sarcastic because we mean it. We just don't want other people to think we mean it.
Sarcasm.
All right. Try the next one. Try the cosine theta.
The worst.
So cosine times sine over cosine gives me just sine. Good? Okay.
That is so funny.
Obviously, because it's math, you know it's going to get a little bit trickier. So now let's look at some fun ones. More fun.
Shut up, Avery. Yay, fun. Are you telling yourself?
So fun. Here we go. I would still start this problem by changing everything to sines and cosines. Okay, so like the tangent of theta. Tangent of theta we can rewrite as sine over cosine. Let's rewrite the secant of theta. Secant of theta is what? 1 over cosine. Minus, well, cosine's already in terms of cosine. Okay. This looks terrible. We're going to be able to simplify this just a little bit, and here's why. I have a fraction divided by something that I'm going to make a fraction. Okay? What I'm going to do, because one of our techniques is to find common denominators, I'm going to find a common denominator for 1 over cosine minus cosine over 1. What would that common denominator be? It'd be cosine. Can't be 1, it'd be cosine. So if I multiply this by cosine over cosine.
Oh, you get cosine squared.
Okay.
This is just
Here's what we end up with. We end up with cosine squared over cosine. Let's talk about why I would do that. If my denominators are the same, what can I do to those two fractions? I can add them, right? I can combine them. So my numerator is still this sine over cosine. Now my denominator is 1 minus cos squared theta over cosine theta. I will tell you I'm not very good about writing my thetas or my x's at this moment. I tend to lose them. Okay, but now I have a fraction divided by a fraction. What can we do now? Copy dot flop. Sine of theta, cosine theta, copy dot cosine theta, 1 minus cosine theta. Look what happens. The cosines go away, right? So we get sine of theta over 1 minus cosine squared theta.
That's it.
Not done.
taking up my whole paper.
This isn't hard.
A lot of memorization.
No memorization. I will tell you when I think something's hard.
Well, you don't think anything is hard.
I don't think, what I think is hard about trig identities, one is your willingness to try it, and two,
I don't have that.
I
don't have number 1.
I think the hardest part about these is that it's not every time you do this. Like we solve an equation, we know what we need to do, right? These are different. And it could be that you started one way and I started a different way. In fact, I could do this problem completely differently and still come up with the same answer.
Completely differently.
Yeah.
Setup.
It's a lot of adverbs in one sentence. This is why I majored in math, people. Not that just
Completely differently. Completely differently.
completely different.
Completely differently. No. Completely differently.
So did you major in
Yes.
and then you didn't graduate to master's?
It was?
No, I majored in math with an emphasis in secondary education, so just a few extra classes. Then I went and got my master's in educational technology, and then I went and got my master's in math.
So like, what made you want to do that? Were you like Just one day, you're like, I really like math. And you're like, I'm gonna become a math teacher.
2nd grade.
Really? 2nd grade.
Mrs. O'Halloran was my favorite teacher.
She alive?
She still is alive. She came to our wedding. Well, she was, I thought,
Like, teachers could be really old when.
2nd grade. I was in 2nd grade in 1987.
Okay, this was only
You were in 2nd grade and when?
1987, maybe?
So you were what, 8?
Is that right? That's what I was trying to guess. I don't remember. I mean, I started
When were you born?
79. Plus 5 is 84. 84, 85 was kindergarten. 85, 86, 86, 87.
Since
clear.
2nd grade, you've enjoyed math.
I knew I wanted to be a teacher.
But not math.
By the time I got to middle school, I knew it was math.
Have you always been really good at math?
I knew in 2nd grade, I never wanted to do math.
I struggled in Algebra 2 Trig.
Okay, yeah, because this is our...
My hardest section in Algebra 2 Trig was logs.
Dude, you have empathy.
Hey guys, tomorrow, or I mean, Wednesday's the last college day.
All right, so let's talk about why we're not done. Notice there's a 1 and a squared. Okay? I want you to go back to our Pythagorean theorem that we should know. There's 1. Recall has a C. Recall. What's the one I said we should know? Sine squared.
Recall.
Okay. That's the one I said we should know. It doesn't quite look like that, but it's close. Could I make it look like that? By doing what? If I subtract cosine squared of x, does it look like that? I would get sine squared x equals 1 minus cos squared x. Yeah? So really, I can take this 1 minus cosine squared x and replace it with what? Sine squared, you mean? Okay. Sine over sine squared. Close. Close to being done. No, but what's sine over sine? 1. So really, watch. Don't write. Just watch for a second. Isn't this the same as saying this? Isn't that the same? Because isn't that sine squared?
Oh, so then they cancel.
Because that cancels out. And then I'm left with 1 over sine squared. Or sine theta, which is cosecant theta.
We did all of that to figure out this cosecant.
Can't you just guess?
It's like a
On Math Excel, if it was multiple choice, I would just guess.
Here's the good news. I didn't give you Math Excel, so you don't get to just guess.
That was not.
I'm
too busy for this.
Okay.
This whole problem took like 10 minutes. That's because it's this one.
You don't want to do the next one?
No. I discount tire.
Okay.
I do.
Tell Elise she can wait for just a minute because class is not done. Oh, it's not done.
Oh, shit.
I didn't say she could walk.
No, I said I should.
have kept on.
Oh.
Right past the path. Right down there.
Then I'd contact your dad. This is the worksheet. I'm going to give you the answers so you know where you're headed.
Wait, this is the worksheet?
This is not the worksheet. These are the answers.
Why are you giving us the answers?
So you can...
Oh, there's a negative 10. That is
No,
so
but the other ones are... These are the simplifying, so that it's harder... Because you're not trying... It's hard to know what you need to get to. Okay. I'm going to hand out your worksheet. Although I think the last one is a good one too, but we didn't do that because